Hello, my name is Reimer Stier, and I'm a member, or I'm an employee of the Mercedes-Benz Tech Innovation. I have to emphasize that. Um, I'd like to warmly welcome you to my project update of the OpenDUT project. OpenDUT, it's the open device under test, but more on that later. On my right side is Stefan Marksteiner from our host, AVL. I'd like to thank you for hosting this wonderful event today, and yeah, it's really great. Well, let's start. I'd like to start with who is involved in this, because it's not just both of us, but there are other members also involved in the project, and then I'll talk about what is it about, and when do we want it, who is interested in this kind of project, and what are the benefits, and what is new. But mainly everything is new because we just released it in December. So, and then I will give Stefan a chance to talk about it, and he will show you how to write a test in his declarative language, and then I'll give a short look out what to expect from it in the future. Well, it's always good to know from who it is coming from. This is a brief slide for our company. I've had it included by our division. And well, I'm from the division Technology and Security. That's an interest aspect, and it's currently two teams that have been merged, and it will be moved to the car division in the future. Okay, so now the more important stuff. The actual members of the project are AVL, CARIAD, ETAS, IAV, and the Mercedes-Benz Tech Innovation. And most of them are focusing on pen testing, the security aspect, and the test and validation part of the component. And we from Mercedes-Benz Tech Innovation focused on the networking aspects and the core components, how this can be orchestrated. And we wanted to give a really fundamental starting point so that we can don't enforce how to add an existing ECU or whatever on open device under test to the network, but to have a very basic communication layer. And what shall it be? What is the open device under test about? Well, it's automation. It's about testing automotive software and hardware, and it shall automate the test and validation process. I'll be presenting later the test components that will actually give the features or enable us to do this. And one of the core aspects is that it shall not matter where they are located, or the hardware devices. You can bring your own ECU and connect it over the internet to an existing test bench, for example, or whatever, and it shall work out of the box, and it should be highly automatable, it should be CI friendly, CI ready, and it should be reliably, securely and repeatably to do this, and form a virtual test bench from a set of configured ECUs. And for us it was very important, because for what I've known, many of the test benches are highly, it's an egg. You create it, but you don't want to ever touch it again. And the automating of the testing and validation process is very important to automate every step of it. So, when do you need the OpenDUT? When you want to test automotive software and hardware, add virtual ECUs to your test bench, connect ECUs from abroad, as I've mentioned earlier, or share hardware between multiple test benches. We have maybe some hardware components that you don't have that much of. It's just a very interesting aspect to share those if they are not used in each test case. You can facilitate tests in a broader aspect and get more of the hardware that you already have. And it should also help test newly developed ECUs with a real test bench. So you have your new ECU and start the integration and testing process as early as possible by connecting it to the OpenDUT network and starting test and validation processes as early as possible and also automating these processes. A few organizational aspects. We've launched this in December. It's in a very early stage in incubating because quite a lot of features are not yet present, but core components were published. We have named it CARL. It's the control and registration logic, and it's the central component that does all the organizational stuff. Then we have EDGAR. It's the edge device global access router, where you will attach your ECU to it. And when I mean ECU, it could be any other hardware. We are currently supporting two protocols, the Ethernet or CARF Ethernet. It doesn't really matter. We are bridging any layer 2 network traffic. And CAN has been recently added to the supported protocols by ETAS. And then there's our front end. It's LEA, leasing ECU access. And then we have also a command line interface that shall have feature parity with the user interface LEA. And there's also a CU that has harness execution operator, which shall give you a CLI to manage the test environment, start up everything that you need to get to know the OpenDUT network or launch a virtual machine that has all the components running in it. And we also published our documentation, and for that I want to do another shout out to the Ankaios project, because we have looked at quite a lot of the workflows and what they are doing. We didn't do it exactly the same way, but it's nice to have another project that is a step ahead of us. So let's see how this is going to be in the future. We will catch up. And the supported protocols I've already mentioned, it's Ethernet and CAN. So what's new since fall last year? We have moved to an initially setup where we have only had EDGAR, now to a managed mode where CARL provides the network and does all the communication necessary to set it up. You can add peers in our UI front and retrieve a setup string and set up a new peer wherever it may live. It does only need connectivity to CARL, and for that we use a WireGuard and do the network connection totally encrypted, and we are using NetBird to do the back-end management for the NetBird and the network traffic. So we are using our CLI to manage a cluster of configured peers. Everything is automated, and for our test environment that is already integrated in the CI integration, that is setting up a bunch of peers and creating and deploying a cluster ad hoc and deploying everything that is required to run OpenDUT, and is pinging all the other peers, so we know that everything is well integrated. And for many of those CI integrations we use CU, that is starting up everything, and for the CI and CD integration and the pipelines we are using Clio, so it should very well integrate with your own pipeline. So if you want to start up a new cluster with OpenDUT, add virtual ECUs or hardware ECUs that have running Edgar next to it, so that the communication can be established. You can configure it to automatically configure all the peers that are required to connect to each other, and set up a cluster of ECUs ad hoc, then run your test onto them, and then send the test results to some backend or whatever. And this is our current architecture. It's a very, very simplified form because we have only 2 edge devices. It just shall showcase some of the features. So we have the UI and the CLI that shall have feature parity, and there's the network management and the WireGuard connection displayed, and the ECU that is attached to the edge device, and the test execution that shall handle the declarative tests, and the network client that is giving the WireGuard network connectivity over the edge devices. Okay, then I'll pass on to you.
Okay. It does work, thanks a lot, and the slides as well. Cool. Where do I switch slides? Oh, there. Okay, thanks. Yeah, so my part is to bring you a little closer to our execution engine inside the OpenDUT project. So what we are thinking about is actually our goal. Just repeat them. One thing is that we want to test on distributed systems on the one hand, but also automated testing with a very, very open and modular environment, so that everyone, as you have seen before, we are very, very different companies. Most of them are big, but still we are living from the community, and everybody has its own approach to test things, and we want to get for that, to attribute for that, and that everybody has his or her way of testing inside our platform. And also we have the problem that every OEM and every supplier and so on has their different systems. I mean, within the SDV community, we are working on convergence, but we don't know if it will ever converge. So right now, at least, it's the case that on every CAN bus there runs a different protocol, more or less. I mean, we have the CAN protocol, but that's only defined to a very low level, and above that, everything's on your own, basically. So maybe all of you know this picture here on the upper left with the Jeep. And we want to test in our system if this attack would work on our car, basically. But we cannot do this because the CAN frame looks different, the software is different, and so on. So therefore, what we want to do is basically abstract the attack, or let's say the structure of the attack, and then feed it back onto the system we want to test. So in principle, that means that in a cyber physical system, as a car is, we want to strip the cyber part and then connect it to your physical part, so that we are basically in a position to be able to test each and every system on the test or device on the test in our project. We want to connect, basically. So what we gonna do here is basically just stripping a working attack of everything that's specific to the device on the test. And that we store in an agnostic manner, technology agnostic manner. So what's looking a bit complicated here is just the thing that we more or less separate the structure, or let's say the things you want to do, the actions you have to take from the data you have. With the data, you can just augment our structure again, and then you can run it on your system on the test, basically. So inside the OpenDUT project, this means that we are contributing to the architecture of the whole system. So every thing in, let's say, cybersecurity engineering stems from the security requirements you actually derive from making a terror or something like that. And this feeds into our test database, of course. And as you can see here on this diagram, just in the upper middle, on the right side, you have the data regarding the device on the test. And on the left side, we have the structure of the attack that you can run on your device on the test. And with those two components together, we can basically compile a real test case again, suitable for this specific device on the test. And that's handed over to an attack execution engine. Also, in the OpenDUT project, this is set up in a modular way. So we have our test or attack execution engine. ETAS and Mercedes might have their own. And also, of course, each of us inside the project is contributing different things. Like one is contributing a fuzzing unit, the other is contributing something more on a high level, and so on. So this means basically that the whole system is modular enough that everybody can use it. Also, the community can contribute, and of course, the partner can make very different things run together in order to automate security. So just to bear in mind, the ultimate goal is that we take away the boring task from the highly paid experts that don't grow on trees, like cybersecurity experts. And we want to actually let a computer do the things a computer can do. We don't need the highly paid experts for, so they can concentrate on the fun stuff, basically. Yeah, and what's coming after that, basically, as you can see, this is a contribution from ETAS in that case. Below on the execution engine side, we have, which you can see some similarities to Reimer's slide before, the execution engine, and then adjacently the low-level stuff. So we have those clients on the edge that you can run your test that's handed over by our JSON format test case file, interpret it and run it on distributed systems. So that's basically stitching together the parts and also pouring in the low-level stuff you need, like concrete testing scripts for fuzzing your system, for attacking it the one or other certain way we define in our abstract language. So for the language itself, it's also a contribution into the project. It's not in the Git right now, just for organizational reasons, but we will be checking it in pretty soon. And also, of course, I want to invite everybody to just have a look at it and play around a bit. But what you can see here is basically a domain-specific language. It's called ALIA, agnostic language for implementing attacks. And what you can see here is that it has mainly three parts: preconditions, like setting up the system; the postconditions, the cleaning up afterwards; and in the middle, the actions, which, just as a DSL should, is just mighty enough to do the job, but not more. We want to overcomplicate things. So the idea here is that a cybersecurity expert looking at such a script here should immediately know what's going on, at least have a clue of it, basically. So like setting up an interface, taking it down, and running a fuzzer or whatever. So in principle, the design of the language means that we just define a set of actions that have certain identifiers, and they would, in the background, when you compile it together with the data from your respective concrete device on the test, would run a certain script, in principle. We're just connecting the data from the device on the test again with the structure of the attack. And of course, for such a language to really actually being able to model this attack, to say, well, this is how the attack runs like on a chip. I want to do the same on a VW or whatever. We of course need some flow controls like if that, then that, and loops and stuff like this. But of course, inside the design, we also wanted to make sure that we don't have anything we don't really need. So just for an example output here, this is what our engine would generate out as a JSON file. And as you can see here, or maybe not because it's a lot of text, it's just basically from the idea that a Linux machine could execute it. But it came in handy to give him some metadata, like run it in a bash, or run it in a Metasploit, or run it in a Python shell or whatever. But this should be something an execution engine can take, interpret, and fire onto a device on the test. So that's already it for my part. I get back to Reimer to conclude the session.
Yeah, the only slide that is actually missing, but you don't have to show it, it's not important, is what is on the road for us. That's the authentication of authorization. That's one big holdback was required to deploy to production. And then a few organizational features in CAL and the test management and the test description language and a few features that shall be put together so we can actually use this. But the OpenDUT network aspect, I think in the next few months that there should be a major release that we can actually use something and connect stuff. But well, let's see when the test manager lands. But yeah, that's it.
Just the last thing to say is, of course, to invite you, basically. Just have a look at the Git, play around, and if you want, even join the project. Thanks.
That would be great.
Okay, thanks a lot. So, are there questions from the audience? Questions? Has anyone tested OpenDUT here? No one yet. So, well, that's a call to action, right? So, that's actually one project that started with a bunch of organizations all working together. So that's actually a great example. Ah, you thought of a question.
I try maybe a generic question regarding testing focused on your project. So if we think about the DevOps loop, okay, where we create, test, deploy, and learn from production, do you think also in production cases where you also some kind, I don't know, trigger or orchestrate even real life software updates, and then you could, or do you have a vision of the DevOps loop? So maybe 1-2 questions in one.
Our vision of the DevOps loop was that you have a definition of the cluster that you want to see, the ECUs that have to be present, or even the state that they have been present in. And we've been looking at a specification language. I don't know if you know Tosca, but it's a description or configuration management that's on top of even Ansible and other stuff, where you can configure each component in what kind of version. We are not actually looking into implementing it with Tosca, but something in between, I don't know yet. It's still in the future. But where you can actually say which components shall be deployed. The CI is running, gets the specification, is deploying the cluster, sees, hey, I need a test bench that has ECU XY, and connects everything ad hoc, and then runs the test cases that were specified for this test. That I think you can pretty much do anything with it.
Yeah, that sounds great, but it's good for development use cases, right? And I think running a baseline update on a full vehicle, right? It's a real hard thing, right? And so I don't expect you to solve that, but a question: how far are we away, and what are your thoughts on that?
How far are we away? Yeah, pretty actually, right now, of course. But that's why we are working on this project. I mean, one thing here is that we try to also have or impose a sort of a top-down approach, so that we are able, with that modular kind of approach, to test a full vehicle as well as a single ECU, and also by providing interfaces at basically every position of the life cycle, which means that you can test a model just as much as a full-blown car, basically. And of course, also with the patterns we create, that you run the same test before and after an update, for instance. So you can do the integration test in that sense when saying, well, I have this attack on the full vehicle. Now I update that stuff and I see if the attack still runs or if I have new attacks and so on. Because of course, with this attack structures, we don't have one. Of course, we want to create a myriad of it. And that means that everything you can probably think of as a penetration tester, we want to test before and after an update. So you test the update inside the car, but also before at a single component or model level.
Thank you.
So any other question before we wrap this up? Questions? No. Okay. So thanks a lot to the speakers, and you'll be here tomorrow as well, right? So great.